Hello everyone, this is the video demonstration for EE452 Lab 2. So in this lab, we create a simple network on AWS and we run some network parameter tests to test the network for its throughput and its parameters. So before that, let's look at our network, which we're going to create on AWS Cloud. So this is a simple network. This is very similar to the one we did for Lab 1. So we have a server, a router, and a client. So we have four subnets. So one subnet is for the server and router side, and the next subnet is for the router and client side, and and two subnets to connect the server to connect the server to an elastic IP, so we can remote login from our host computer, and similarly for our client. And the wireless router is also done through 10.0.1.0. So this is like a more clear explanation of a subnet. So this is the server router subnet, and this is the client router subnet, signified by the CIDR block 10.0.2.0/24, and the server router subnet is signified by the CIDR block 10.0.1.0/24. So now let's go to AWS and create a network. So we are currently in AWS, and we've got to create a VPC, that's the virtual private cloud, for our network. So we already created a VPC call and named it Lab 2, and we have given the subnet the CIDR notation of 10.0.0.0/16. So now we have this VPC. We got to create four subnets within this, as previously mentioned. When you go here, we have these four subnets. So this particular subnet, server subnet and client subnet, these subnets are to initiate remote login from the outside world. So we basically bind the elastic IP to this particular subnet, so we can so this particular so the whole system can be so TCP sorry I mean SSH communication can be initiated from the outside world. Yeah, and we have subnet 1 and subnet 2. That's part of the actual network that includes the router. So if you see here, we have the subnet 1 and subnet 2, and the same thing we've created in AWS. So now we have this, we got to create an internet gateway, so our VPC can communicate with the outside world. And we have already created an internet gateway for Lab 2, and we've attached it to the VPC as seen here. So now we have this, we got to go to route tables and actually formalize this connection. So when we go here, and let's go to routes, so we can see our destination is 0.0.0.0/0. So this is basically all public IP addresses, and the target is going to be our internet gateway. So this means that so our particular VPC can communicate with the outside world. So that's the basic explanation for this. So now we have created our basic network. We got to create the Amazon AWS instances. That's the server, client, and router virtual machines. So let's go there. So let's go to instances. So you can see we already have a AWS instances for the server, client, and router. So the server and client run on are basically Ubuntu virtual machines, and the router is a iOS machine. So let's just see how it's done. So I'm going to go to launch instances, and I'm going to create a server instance for this particular example. So I'm going to name it server video, and this OS image is going to be Ubuntu. So we got to search, and we're going to choose this particular image, and this is going to be T2 micro, and the keypad. So we're going to create a new keypad. So this particular keypad is basically for security reasons. So we download a private key, Amazon holds the public key, and let's say I'm going to initiate SSH communication from my host computer. So I'll be having the private key, and I'll use that to communicate with the AWS instance securely. And I'm going to name it server video key. Yeah, so we have that. I'm going to create a new path. and we're gonna make changes in the network settings. So so this particular Amazon instance is gonna be inside our lab to VPC. So that's here, and the subnet is gonna be, yeah, the server subnet, and we're gonna add security group rules. So it's gonna be all TCP, and 0.0.0/0 is gonna be all the public IP addresses, and it's gonna be all UDP, again 0.0.0.0, and all ICM. So we have network interface 1. So this is in the subnet of 10.0.3.0/24. So this particular network interface 1 is going to initiate our remote login from the outside world. And we're going to add the new network interface. And this network interface is going to be in the subnet of 10.0.1.0. And it's going to be the actual virtual network that includes the router. So the subnet is going to be subnet 1, and we launch the instance, and the server instance, or in this case server virtual machine, will be created in the Amazon cloud. So similarly, we can create the client and router instances using these methods. So now that the instances are created for the server, client, and router, so let's start them. Okay, so we have started these instances. That means the virtual machines are running inside our virtual network. So now we gotta bind elastic IP addresses to these three machines, so we can initiate remote login from our host computer or anywhere from the outside internet. So when we go to route tables and go to elastic IP, and I'm gonna allocate an IP address. So, and this we gotta associate the IP address to a particular network interface. So we're gonna attach it to the server for this example. So when I go to server and I go to networking, so we can so as mentioned, we have seen that we have to attach the elastic IP to this particular subnet 10.0.3.0/24. So, and this is the network interface 0 for this for the server instance, and so this is the IP address we're gonna bind it to, and this is the network interface 0138. So let's do that right now. So the network interface, and we can see we have the 0138, and the private IP is this one as seen. So we're gonna associate. So when we associate this public IP address to the particular network interface with the private address of 10.0.3.115, we can initiate the SSH communication. So let's do that right now. So the private keys are downloaded in this particular folder, and let's start. So first, let's ping the public IP address. So I can do ping. The IP address is, so we can see we get a ping back. And now let's initiate the SSH communication. So it's going to be SSH. The name of the private key. In my case, I named it server key. And the public IP address. Yes. So yeah, so right now we have logged in remotely to the AWS instance. In this case, the server. And we can see when you go to instances, let's refresh the page, and we can see it has the public IP address. That's the elastic IP address we associated with this particular server. So similarly, this is done for the client and router. So let's do that, and then we can start testing. So we have created 3 elastic IPs, and we have binded to the 3 machines: client, router, and server. So now let's go to our command terminal, and I've already initiated the SSH communication, as you can see here. So this is the server, and this is the command, and this is for the client. You see we have logged in, and this is the command, and again for this router. So this is the router, so we have logged in, and this is the command. So now we have logged into 3 machines. So let's try to ping the other. Let's try to ping the network to see if the connections are established and actually working. So now let's go to the server, and let's try to ping the router. So I'm going to do ping, and so I'm going to ping this IP address. So this, because this one interface of the router, and it's in the same subnet as the server. So I'm going to ping 10.0.1. So we're getting a ping back. So connection is established with the router or subnet. And also let's do the same thing for the client. That's communication with the router. So let's do ping 10.0.0.2/47. Again, we're getting a ping back. So, but let's try to ping the client from server. So let's look at the IP address of the server client. So the installation has to be done. So now that the packages have been installed, let's try to ping the client from the server. So I'm going to ping and define the IP address of the client, and you can see this is the IP address of the client. So we can see we're not getting a ping back, and that's the reason for that is because the route has not been added for this particular path. So let's do that right now. Stop it and let's add the path. So I'm going to add the path to the client from the server through the router. So now let's go to our router, and we can see these are the IP addresses of the two network interfaces, and these are the gateways for each of the server and the client. So this subnet 1 is going to be the gateway for our server, and the other is going to be for the client. So I'm going to do, so this is going to be the client side subnet 2, the gateway IP address. So it's going to be 10.0.1/22980, and it's because the Ethernet port 1. So we can see the IP address 10.0. Oh, I've got to go to the root. Sorry about that. This is done, and let's do it for the client. And the gateway is going to be, oh, I'm sorry. Okay, so now this is done. So now let's try to ping the client again. made a mistake. Yeah. Yeah. So I made a mistake. So I did the route improperly. So now we're getting a ping back from the client when we do in the server. Now again, let's try in the client side, trying to ping the server. And I'm getting so our IP address is over here. So this is the server IP address. And we can see I'm getting a ping back. That means it's working. So let's also trace route to see the path it's going to take. Yeah, so we can see from the client is going to the router subnet from the router. Then again from our router is going to the host. So now the connection has been established. Now let's do the IPRF measurements. Start with the IPRF measurements, and let's start on the server side. So now again the client. So first let's measure TCP throughput. This is the IP address of the server. And let's go, let's say. So I'm getting a TCP throughput of 1.23 gigabits per second. And let's try UDP. So I'm getting a throughput of 1.3 gigabits per second for UDP and 1.23 gigabits per second for TCP. Most importantly, let's look at the losses. So it's had UDP has lost around 2.2% of the packets it has sent. So what we're noticing is UDP is actually much faster than TCP because it doesn't care about reliability. It's all about pushing out data as fast as it can. So we can see UDP is faster than TCP. While in this case it's by a less margin, and theoretically it's going to be much more. UDP is faster than TCP. So now this is done. So let us introduce impairments in our network. So the first one is going to be a delay of 100 milliseconds from the server and the client side. So let's do that. Okay, now let's start. The first one we're going to measure the TCP throughput. So we can see the TCP throughput has reduced by huge amounts, almost 10 times. So let us see the final throughput we're getting. So the final throughput we're going to get is 100 megabits per second. So then now the reason for this decrease. So since we're introducing a delay of 100 milliseconds, so when TCP is running and a particular, let's say the sender doesn't receive the ACK and timeout occurs. So then the sending rate is gonna reduce even more according to the TCP protocol, and this causes a huge hit in the throughput. But we can also try UDP. And so we can see UDP throughput from this side. So we're getting a throughput of 651 megabits per second. So we can see UDP throughput doesn't have a strong hit as compared to TCP. This is because UDP doesn't have any of the congestion or flow control protocols, and the only impairment here is the delay. For TCP, it's going to be the delay as well as congestion control that further reduces the sending rate. So now this is done. So the next one is we're gonna introduce a packet loss of 10%. So let us introduce 10% packet loss in our network. And same thing over here. And let's start. This is going to be, we're going to measure the TCP throughput. And this is the throughput we're getting. So we're getting a bit rate of 12 megabits per second. So we can see the 10% loss has taken a huge hit from the initial of around 1.2 Gbps to only 12 now. So since we have this, now let's try changing the MTU, that the maximum transmission unit size, and we can see the change. So right now, the MTU size is set to jumbo. That's 9001. So you can see here. So we're gonna try to change it to our the default normal one. That's going to be 1500. So let's see what happens to the throughput then. But before that, let's also take a look at the UDP throughput. So we'll get interesting results. So let's look at the UDP throughput. So we can see the UDP is going to be the same as before, around 1.2 gigabits per second. Now, what's the reason? This is because UDP doesn't have any reliability. So even if there's a packet loss, it doesn't matter for UDP. You're still gonna get the same throughput you get initially. But for TCP, when a loss occurs, TCP goes into timeout, and then it again retransmits the particular packet. So none of that happens in UDP. So the packet loss doesn't cause any impairments to a transmission UDP. So we're getting the same throughput as before. So now let's change the MTU size. Okay, so again we're going to change it in the server side also. So now we have changed the MTU from 9001 to 1500. So we can see here, and here. Now let's try the TCP throughput while introducing the loss of 10% again. So let's start. Okay, so now let's look at the throughput. So previously when the MTU was 9001, the throughput was 12 megabits per second. So let's see what's happening here. So we can see the throughput is only 3.01 megabits per second. Now, so the reason is as MTU decreases, so basically as MTU decreases, the throughput also decreases. Now this is because let's say when the MTU is very small, and when the packet success occurs for the 10% loss, only proportionally less amount of data successfully received. So that's why the throughput is proportional to MTU in this case where we introduce loss. And then in the next case, we're gonna limit the rate to 100 megabits per second. So let's do that. So first let's change the MTU back to normal. Again, the same changes are made in the server side. And now let's do the next impairment. So we did the next impairment, that's capping the rate at 100 megabits per second. So this is the particular command. And when we did this in the server and the client side, we, are, we can see the TCP throughput didn't exceed 100 megabits per second because that's the cap. And we got throughput of around 91.1 megabits per second. So the next thing, instead of making the changes or impairments in the endpoints, that's the host and the client, we are we are we are setting impairments in the router. So we have done it over here, as we can see. So we can see we have introduced the delay of 100 milliseconds instead of the endpoints, but right now, but in the router. So let's see if the throughput characteristics were similar to the ones where we made the changes in the endpoints, or let's just see what happens. So let's just see what throughput we're getting. So if you remember correctly, we got around 102 Mbps for, for the change for the impairments in the uh, endpoints, but for the impairments in the router, we're also getting a very similar value of 98.9. So we can see the changes in the impairments in the endpoint is very similar to making a single change in the router. Now this is because this is the only traffic in the whole network. Only these two endpoints transmit traffic through the router in this particular case. So that's why we're getting similar values. But in the case of where the multiple endpoints and multiple hosts are connected to the router, these particular changes can differ. So that's lab 2.